This is the CapEx IndustryCast. And what the IndustryCast is every week at 11:30 Eastern time, we go live to talk about a technology, either emerging technologies or existing technologies that can help our customers in the manufacturing world manufacture parts better or have better manufacturing processes. That is our mission. So we've done multiple conversations about leak testing as an example. We've done lots of conversations about plastic joining. Today, we are fortunate to have Paul Cathcart. He is from Duquesne. He is our tooling engineering manager, been with Duquesne for many, many years. He's got great energy, and I'm always excited when I have an opportunity to talk with Paul. I get all pumped up and excited about whatever it is. He makes this stuff sound so interesting and gets us energized. So today we're going to be talking about, as you can see on the screen, emerging technologies for particulate free welding. And so we'll be digging into some of the ideas, strategies, methodologies that we've been applying at Duquesne to help us put these parts together without creating a great deal of debris. So with that, Paul, what did I miss there?
No, I think you did a pretty good job, Russ. I appreciate the intro. It sounds like I've got some pretty big shoes to fill after the way you sold me there. So I'll do my best to stand up to that. So this is kind of a broad presentation I have, and there's a little bit of history of Duquesne here. If you'd like, I can skip through this in the interest of time. Really, all you need to know is we've been welding plastic for almost 100 years, coming up in 2022. So believe it or not, we kind of know what we're doing. I'd also like to add that we offer the widest range of plastic welding equipment of any welding company in the world. So what that means is we're not going to give you the best piece of equipment that we have to put your parts together. We're truly going to give you the best product to do the best job that we can and give you the best chance of success. So yeah, if you could just kind of pop through here, Russ.
Yeah, absolutely. That's excellent.
You can skip the video if you want. We'll go through that.
Your global organization.
Yep, global organization. We're in almost every continent. So we like to say one world, one Duquesne, and we truly mean that. We can work with your companies seamlessly wherever they're at in the world. I want to cover briefly the products that we offer as a whole. So everybody knows we sell ultrasonic welders, both pneumatic and servo. That's kind of our bread and butter. We also offer spin welding, thermal forming, and you can think of that like hot air, cold state kind of, electromagnetic resistance or induction insertion of metal inserts, hot plate and infrared welding, hot gas welding, vibration welding, and laser welding. You could shoot ahead there.
All righty.
What I want to focus on today, it seems like the big buzzword in the industry is particulate free welding. And there's a few technologies that really stand out when we're talking about that subject. And they are infrared welding, hot gas welding, laser welding, and infrared preheat vibration welding. The benefits of particulate free welding basically are that they give you stronger welds than conventional processes. In most cases, they're non-contact, so we're not going to risk stringing material. We can focus the energy on the weld seam to give you a really clean weld. We can reduce stress in the weld joint. Obviously, if it's particulate free, we're not going to have any contamination. And it's a good looking part because we're not particulate free and we're not producing flash.
So I have a question for you, and you may get into this as we move along here, Paul, but how does it make stronger welds? What is that part of the presentation moving forward, or?
No, it is, but I can touch on that briefly. There's a couple different reasons. One with hot gas welding, that's basically a form of thermal welding. With basic hot plate and IR welding, we run the risk of either reducing material that's coming together in the joining phase or oxidizing or degrading the material because of the high heats used in infrared welding. With hot gas welding and with laser welding, we kind of isolate oxygen from the weld joint, thereby giving you stronger material or reducing the risk of reducing the strength of the material when we put it together.
I see. Okay, so this is one technology here is infrared.
Yep, infrared will be the first technology we focus on. And Russ, if anybody has any questions here, anybody feel free to jump in anytime. I can offer more information. I'm going to kind of do a top level overview here. But infrared welding, as you just saw in that video, is basically like hot plate welding, only we're not touching the part. We're using a very high intensity heat source to melt the plastic and then stick it together. So if you can shoot ahead there.
All right.
I'll discuss these as we go on. I'm going to kind of skip over some of these. So the basic benefits of IR welding are, it's particulate free because we're not touching the part. Conventional hot plate welding has been around forever and it works very well. It's very reliable, but we're touching the part to heat the surface, and we're using a non-stick coating like Teflon to try and prevent material stringing. And we're also consuming some of that material when we're contacting it. With IR, because we're not touching it, we're not consuming that material, and all of it is left to be used in the joining phase. And because we're not touching it, again, we're not pulling any particulate. Infrared welding, like hot plate welding, gives us the ability to weld very complex contoured parts. So if you're thinking, complex assemblies, very tall walls, lots of curvature, you want to go down the thermal welding road. As I'd mentioned, less rigid materials, with tall walls, because we're not vibrating them as we do in frictional welding, we have much better success using thermal welding.
Yeah.
And because it's non-contact, we don't have to deal with Teflon maintenance. And hot plate welding, typically every 2 weeks to maybe every month, unfortunately, you've got to pull platens out and recoat the Teflon. Anybody doing hot plate welding is probably aware of this. If it's a flat part, sometimes we can get away with a Teflon film to prevent stringing, but if it's contoured, you definitely have to do the maintenance that we're talking about. So there's lots of different ways to produce infrared heat. We're doing something a little bit different than most people out there. There's ceramic carriers with embedded nickel chromium foil. There's mineral insulated cables, and every one of these methods has their drawbacks. And we'll kind of go through these as we go forward. One of the biggest problems, one of the most common solutions out there that people are using, and we tried doing this for 3 years, is this contoured soft ceramic heater with a potted in kind of like toaster element. And the problem is that these soft ceramics break, particulate ends up in your assemblies, and these elements can oxidize. We tried for 3 years to overcome some of these problems, and we weren't able to do it. So that's why we went down another road from what people are doing. And we've talked to a lot of customers out there that are using these current solutions, and they're finding they have the same problems. That picture that you saw is an example that's very common, a cracking heater. So the foil emitter that is most commonly used works in the medium, if you keep clicking through there, works in the medium to long wave infrared spectrum, which means that you have to have your part within a millimeter or two of the heater to evenly heat it. The problem with this is if your plastic part is perfect, that works pretty good. But every once in a while, we have variation in molded parts. I don't know about you, Russ. Do you see variation occasionally?
Yeah, right.
So
everyone's the same. Every part that our customers mold is exactly the same.
There you go. Then we shouldn't have a problem. This method will work great. But if you do have variation, it becomes very difficult to produce a consistent heat on the weld front. So if you move ahead here.
Sure.
Yeah, you can keep going. We won't bore everybody with the details.
Yeah.
Basically, what this means is we've got to be within a tolerance of plus or minus 1 millimeter. And if your part's warped, as I'm kind of illustrating here, you can see you get significant variation in the melt front, and that causes problems. So if we move ahead.
Yeah, some hot, some cold, or some melted, some not.
You got it. You got it. So we're doing something a little bit differently. What we're doing, we're working with a supplier that is very good at making custom contoured shortwave emitters. And they've actually allowed us to design our own emitters, so we can custom design these emitters to match your application perfectly. If you move ahead here, basically what this means is we're working, keep clicking ahead here, in this shortwave infrared spectrum. So as we move ahead through the slides, you'll see they're very similar to the previous ones, but basically what this means is we can heat up to 15 to 25 millimeters away, and we can absorb almost a full 8 millimeters of variation while maintaining a consistent melt front. This makes it very easy to deal with molding variation, part size variation.
It's much more forgiving, it looks like.
Much more forgiving, exactly. So the bottom line is, think shortwave emitters. you can absorb a lot more variation, you know, maybe up to 8 millimeters versus foil emitters that are out there. You can maybe absorb a couple millimeters of variation. So this is an actual example of a heater that we've done for a part. And you can see how we would mount this heater in there. And our competitors will tell you, okay, that's all well and good and it works good, but these things are kind of expensive and they're kind of fragile and you're going to break them a lot. So if you move ahead here, we have an answer to that. We've developed custom contoured shielding that fully protects the heater and can withstand the full impact of the machine. It's water cooled, so it's safe for the operator. You can actually touch it right after a weld cycle. And then we have an aperture that exposes only the area that needs to be melted to the plastic part.
Yeah.
And just so you don't think we're showing you pretty CAD pictures of something we've never actually done, here's a photo of that actual heater in production. You can see what our heaters work like here. And our customers love these things, again, because they absorb so much variation and still work well. And it's really difficult to crash them, you know, as compared to some of the other solutions in the industry. And I should add that we use the same heater technology in both our infrared welders and our infrared preheat vibration welders. So any questions so far? Yeah.
That sounds great. That's awesome. Is it 10 times more than the traditional, or what, from a cost perspective? Sounds like there are a lot of technical benefits. What's the impact on the pricing?
You know, pricing is maybe, you know, machine cost is about the same. Tooling goes up maybe 25 to 50% over the current solutions out there. But what we're finding on the backside with maintenance, it more than pays for itself within the first year of production.
That makes sense.
So this is just a picture of a video, I think, if you click on it, if I remember right here.
Oh, yeah.
A video of one of our infrared welders running, and you can click on this to go through a little faster if you like. But in case nobody's ever seen an infrared weld, this is it running, welding a very large tail light. So we all know tail lights are pretty contoured. You can see an actual weld process here. Now, I want you to think about what you're seeing here going forward in the presentation. You're seeing a little smoke, and that does happen quite often in infrared welding. And that's one of the drawbacks. In a lot of cases, it's not a problem, but sometimes to get the full depth of penetration that we need, we burn the surface a little bit. And in clear parts, maybe we get a little discoloration, and sometimes maybe we get a little reduction in strength to be completely transparent. But in most applications, it's not a problem. And if it is, we have other technologies that solve these issues going forward.
Oh,
you can bounce to the next slide here. Yeah, you can skip through all this. This is boring control stuff. Really, all I'll say about this is if you're going to get a hot plate welder, an infrared welder, or a hot gas welder from anybody, you can stop here. You're going to buy 3 different machines. You know, if you're already hot plate welding, you can't put an IR tool in it. If you want to go into IR, but you want to run your legacy hot plate tools, you usually can't do it. We've hybridized the control systems, and we offer what we call the TH3 welder. That was the welder that you just saw there. And that means thermal hybrid 3. So what that means is you can run a hot plate tool, you can run an infrared tool, and with a couple of add-ons, you can run a hot gas tool. And I'm sure many of you don't know what that is yet, but you will by the end of this presentation. So 1 machine, 3 technologies. It's a great way to move forward if you want to step up in technology.
I mean, that's really unheard of, right? Because normally you buy a hot plate welder, or you buy an infrared welder, or you buy a hot gas welder.
You've got it. That's the key point. Exactly. So can our people watching, if they have any questions, can they ask? Or
yeah, they can certainly ask. There's in the there is a notes area. So Vicki, the only request that I have there is if anyone does ask questions, Vicki, just let us know, if you would, please.
Yeah, all right, absolutely.
Okay,
but you're doing a great job covering the questions, Russ. I appreciate it. You make this easy. All right, so people always ask us, how can we infrared weld faster? So I won't bore you with all the details here, but basically we've made a rotary infrared welder. So you can be chucking in parts, have them melting at the same time, and have them testing and coming out the back end simultaneously. If you move ahead here real quickly, basically what we've done is, you know, if it takes 20 seconds to melt your part, that means the fastest we can index that table is close to 20 seconds. But if I have 2 heater zones on my rotary table, now I can index every 10 seconds. I still get a cumulative 20 seconds of melt time, but I'm chucking a part out every 10 seconds instead of 20 seconds. We call this melt division, and it's made for some of the fastest infrared welders in the world. We have production systems out there that are producing a fully infrared welded part in an 11-second cycle. And
Wow.
we're doing laser marking and inspection.
What's the envelope of those parts? At what size?
You know, I would keep the parts under probably 8 inches square and maybe 3-4 inches high. We could do custom, but that fits our standard system very well.
Sure.
Here's a picture of it. You can keep going here. Keep going. I think we've got a video somewhere. This just kind of shows one of the advantages. Actually, if you back up once, no, we'll show this. You can see this thing running. Okay, yeah. So the other thing that this rotary gives us the ability to do, in most welding systems, you're shuttling the heater in and out, and that inertial motion can sometimes reduce the life of the heaters. By using a rotary, we're taking the rotary motion to pass the parts over the heaters, keeping the heaters stationary, which drastically improves the life of the heater. In many cases, we get 4,000 hours plus of life out of our infrared heaters. And I will say the vendor that we work with has a fantastic policy where if there's any failure under that time that's not due to an impact or something, they'll cover the emitter.
Wow, good supplier.
Yep. So here's a video of one running. How are we doing on time here? I guess we're still okay.
I love the music.
The music's terrible. Marketing added that in on me, and I'm always turning it off. Fortunately, I'm not hearing it coming across here, and I hope our participants are not as well. But you can see this welder running. You can see the heaters in the background, the rotary action. You'll probably see some goofball running the welder in a minute here, and that's actually me. But
You're famous.
I wouldn't go that far. You can see it's a very compact machine with a lot of flexibility. We've got quite a few of these out in the field now, and customers have had nothing but good to say about them. You can probably advance ahead in the interest of time if you like, or if you're intrigued by this, we can go through the video.
Yeah, no, that's very cool.
One other thing I guess I would add on this video, you can see there's a couple of operators in this case. This assembly was so complicated. There were 6 or 8 parts that needed to be loaded. We actually had multiple load stations to keep up. So we had maybe one person loading parts and a switch and another person loading cables and internal components, and that enabled us to meet the rate we were looking for. We also will add in integration to interface our machines with a custom robot or a collaborative robot in many cases, if that's something you're interested in doing.
Wow, very cool.
All right, what else? Infrared preheat vibration. I'm gonna make the assumption, in the interest of time again, that most of us know what vibration welding is. Basically, you rub parts together, they get hot, and we melt them together. So infrared preheat vibration, we add these infrared heaters, we preheat the surfaces, we pull the heater out, and then we vibe weld them together. So many people ask us, gosh, if you're already in there, why are you not A, just infrared welding it, or B, just vibration welding it? And the bottom line is, with vibration welding, we produce some loose particulate because we're rubbing 2 cold surfaces together, and sometimes particulate comes off before they melt. And with infrared welding, and this is why I asked you to remember that previous movie, sometimes we degrade the surface and weaken the part a little bit. So by combining the processes, we put just enough infrared energy into the surface of the part to get it to a plastic state without degrading it. And then we finish the weld with vibration without getting particulate because we're already at that plastic state. Additionally, with glass-filled materials, because we're vibing, it gives us the ability to get a better intermix of that glass strand at the weld surface, making a stronger part.
Makes a lot of sense.
Yep, certainly. You can bounce ahead here and we'll see what we have. This basically says most of what I just told you, so we'll skip through that. Here's a video of one running. I think you're going to be hearing that wonderful music again. But this is our typical preheat vibration welder running a set of lamps. So you'll see these heaters come forward when he cycles the machine. We preheat the weld with the infrared. So we clamp up, we preheat. You can see the heaters fire, and then we'll retract and vibe weld the part. And while you're watching this, I'll add another key point. A lot of our competitors have separate heater assemblies and separate cold vibration tool assemblies. We take a unique approach where we actually mount the heater assembly and drive unit onto the tool. So it gives you the ability to change out the entire heater and tool cassette, making it very easy to change parts when you're running. Additionally, we can turn off the vibration and we can do straight infrared welding, and we can remove the IR and do straight vibration welding. So again, we're talking hybrid technology. You get the infrared control upgrade. You can do IR, you can do IR plus vibe, and you can do straight vibration welding in one machine. And we do have several customers doing this right now.
Yeah, very flexible.
Yeah, yep. So I think if you look at this slide, you move ahead. Why do we use infrared preheat? It's to go from flash that potentially looks like the left, which we've all seen, to flash off a vibe welder that looks like what you're seeing on the right. And obviously, I think we would all take the right over the left any day of the week.
It's like toothpaste.
Yeah, there you go. Exactly. So back to what I was saying earlier about why we get particulate. We're using friction to heat these parts up and melt them. So before it melts, we're scrubbing particulate. And that's what you're seeing illustrated on the left before that melt on the right is initiated. And I think if you go a slide ahead, I may have some cool stop action video showing this. So this is really only 2 to 3 seconds of weld in this video, but we used a high-speed camera to capture the actual vibration. So that you may not see it, but there's a little particulate coming off the entire time on the right. It almost looks like dandruff coming off the weld. And that happens during every normal weld. And you can see now the melt's initiated and propagating out, and the particulate goes away. But that, in a nutshell, is why we use preheat vibration welding to reduce particulate. So I had mentioned we use the same IR heater technology in our IR preheat vibe tools, and we combine our heater assemblies directly into the vibe tools so you can change them out as a cassette. That's what you're seeing here. You're seeing a servo shuttle and a completely water-cooled, shielded emitter array built into the vibe tool in the extended and retracted state. And again, so you don't think we're just showing you little CAD images of something we've never built. Well, coming up here eventually. Oh, here's a good cross section again, showing how we protect the heaters inside of that shielding, and then how we have the apertures just exposing the areas we want to melt. And then if we go ahead one more here, you will see, yep, very good. And if you go ahead one more here, you can see an actual heater for that lamp powered up. And here's some other examples just to show you the complexity of tooling that we can do. Here's some more lamp tooling, IR preheat vibe lamp tooling. Here's an entire cross-car applique. And just in a nutshell, you know, what I'm showing here is really no matter how complex the part, we generally can come up with a solution to weld your part. Keep in mind, this guy is probably 1,200 millimeters long.
Wow.
It's a pretty significant tool.
Was it for a bumper, or what was that?
That's a cross-car applique, I think on like a Dodge SUV. If I'm not mistaken. So
what's a cross-car applique?
That would be the rear lamp that goes all the way over the lift gate on an SUV.
Yeah. Okay.
Or on the back of a car, and your side lamps would be mounted to the ends of them.
Gotcha.
All right, hot gas welding. This is one you've heard me mention. Again, it works exactly like hot plate and IR welding, but the difference is we don't degrade the material. So this is a technology developed by a company we purchased. They've been doing it since 2005. It's a great company by the name of KVT. And their problem was they have a popular product and they're not large enough to support it globally. We have the global footprint, but we don't have the technology. So it's a marriage made in heaven, right? We give them the support and the marketing footprint they need, and they give us the technology and the ability to build these things. So now, rather than these just being built in Germany, I've managed to train up our North American engineering team to design these tools so we can do that domestically for North America and Mexico now. So if we move ahead, let's see what did we lock up? Oh, okay, we've got a video again. So we'll show you hot gas welding. Probably more of that lovely music again. And here we go, maybe. Okay, so you can see the heater coming forward, but instead of seeing IR bulbs or a plate, you're seeing lots of little needles. So what we're doing is we're passing superheated nitrogen through these needles, producing a laminar flow to melt a very complex weld seam, as you can see here. Now, the benefit of this, with a hot plate tool, if your plastic part varies, we can't adjust it to match the contour. With an infrared tool, because the bulbs are quartz, we really can't adjust it to match your part contour. With a hot gas tool, we have all the benefits of those previous two technologies, but we can actually bend these little needles around very easily to perfectly match any variation in your plastic part. It is the only non-contact, high-temperature welding method in the world that can be adjusted, and the benefits of this are phenomenal, especially when you start doing things like intake manifolds for cars. Anybody who works in that industry, they know how much variation that you see there.
Yeah.
So if we move ahead a little bit here. So the benefits of hot gas welding, again, it's particulate free. The key to this is it does not oxidize. And I'll get more into this going forward, but the nitrogen keeps the oxygen away from the weld joint, just like a MIG welder uses a shield gas to keep the metal from bubbling. And it's a non-contact process. You probably want me off of here pretty quickly, don't you?
No, you're good. So how are you heating the nitrogen?
We'll move ahead here and we'll get into that a little bit.
Oh, okay. All right. We're still looking at.
I've kind of touched on these points as I'm talking. Yeah, we can blow through them here. So we use nitrogen because it's the most prevalent inert gas in the atmosphere. So we have a nitrogen generator in the machine that pulls the gas out. And then if you move ahead, we use, maybe it's ahead one more slide. We basically create something like a hot runner. I'm sure most of you are familiar with hot runners and injection molds, but instead of passing plastic through the hot runner, that's what we call the serpentine plate here. We have runner zones where we pass the nitrogen through, and they're heated by the heater plate to bring the nitrogen up to somewhere in the realm of 700 to 1,000 degrees Fahrenheit. And
Wow.
we have up to 60 control zones where we can very accurately control the gas flow, thereby increasing or decreasing the heat on every one of those, up to 60 zones that we're using. So there's very finite control, and there's adjustability, and there's no degradation of the plastic. This is, hands down, the cleanest, most versatile welding method out there right now. So if we move ahead one more screen here, I think this is the key. That's not the key slide. Okay, that's more examples of cool heaters. This is the key slide. So this is a nylon part on the left where we've done a melt map. And everybody knows with hot plate welding, a melt map is when we bring the heaters in and we contact the part, and then we interrupt the joining phase to see how accurately our part is melting to make sure it's ready to be joined together consistently. So the left, you can see it's a very clean, nice looking part. That was heated running the nitrogen through the heater. On the right, it's the next subsequent part, but we turned off the nitrogen and we just ran compressed air. You can see the impact the oxygen has on the weld seam. This is why it's so critical to use nitrogen in the heating phase.
Wow.
Yeah, because we're in an inert field, we can melt as much plastic as you need without ever degrading it. So like again, an intake manifold where you might have a 5 millimeter wide weld bead, we can melt all that plastic and put it together.
Wow, that's amazing how hot that gas comes out. So those heating platens, like what are they made of?
Stainless. It's all like a 420 grade stainless. And then we have cartridge heaters in there.
Through induction?
Cartridge heaters, resistance cartridge heaters.
Okay. Wow. How long does it take to get those? So if you were to walk in, the machine was cold and you needed to start making parts, how long would that take?
That's a great question, Russ. It's very similar to a hot plate in that sense. You probably have a half an hour to 45 minutes of warm up before you can start production. The machine does have timers, so you can set a clock so it starts preheating before shift and is ready when people arrive. Now the advantage again with infrared is it's instant on, right? We come in, we turn the welder on, and bam, we're up and welding. So we don't have to wait for that heat up time.
Sure. So these are just examples.
Yeah,
of
this just
pictures.
shows, we can do all the things with tooling people want to do. Scanners, barcode readers, all sorts of things. This is kind of an interesting slide. With hot gas, we get such a thorough melt. When you injection mold long strand glass fiber parts, there's stress in the glass. We can get such a thorough melt with hot gas welding without degrading the material. You actually see the glass rise up at the weld joint. It almost looks like a cake rising. And the benefit of this is because those fibers stand up, we again get that intermixing of the material. Exactly. Thank you for the illustration. Yes. And this gives us 100% parent material strength in glass filled nylon, which we don't see in any other process.
Wow. Very cool.
Yeah, definitely cool. This is just some examples of parts that we weld. Quite often we're doing under the hood components and most of the materials associated with under the hood components.
As well as door panels and dash.
Yeah, we can do door panels, we can do lighting, you name it. I would say, come to us early on in the phase. We offer as a free service design assistance. So if you have a part, you want to put it together, you're not quite sure what you want to do, we'll help pick the process and we'll help you design your part at no charge to make sure you have the best chance of success. That's one of the things our customers really find appealing about us. And we offer what I like to call art to part. We'll work with you right from the product design phase up through tooling design, machine build, and all your runoffs until you're satisfied, all done under one roof without parts going in and out to subcontractors. So this screen is showing a microtome of a hot gas weld. You can see the lack of color at the weld seam, which means there's no stress. We've annealed this part as we've been welding it. All right, let's see what's next here. Do I have time to briefly go through laser?
Yeah, let's talk about laser welding, of course.
All right, cool. Laser welding, in a nutshell, is passing light energy through a part to produce a melt at the weld zone. It's a great process. It's very clean. If you move ahead, we offer 2 different laser welding technologies. I guess we've got advantages of laser welding. So again, it's particulate free.
Again, that's what we're talking about.
Yeah,
today.
Near parent material strengths. We reduce the stress. We've got super accurate control. So it's amazing how accurately we can laser weld, and it's very repeatable for high production. And it makes good looking parts, of course. So if we move ahead here, you don't need to go through.
Man, lots of benefits.
Too many points on there. Okay, so there's 2 different welding technologies. There's 1 micron and there's 2 micron. That's really all you need to remember. In 1 micron welding, we pass through a laser transparent part, and then we hit a laser opaque part, producing a melt that radiates back up into the transparent part. So basically think, to keep it simple, clear to black. It's the most common laser welding method out there. So if we move ahead to the other welding method, 2 micron laser welding. Basically what this means is welding laser transparent to laser transparent. And I make that distinction because a lot of people say, if I can't see through it, it must not be transparent. Well, that's not true when you're talking about lasers. Just because you can't see through a part doesn't necessarily mean that the laser of this given wavelength can't pass through it. Nylon is a classic example. You can't see through it, but it is absolutely laser transparent. So before you decide what you need, come see us and we'll tell you which application is right for your material. But in a nutshell, again, think 2 micron clear to clear, basically. We see this in a lot of medical applications. So this again is another microtome slice showing a 2 micron laser weld. And it is very clear how we pass all the way through both parts with this welding method.
So how does the weld take place? So we're not, it's not welding like this. It's still the laser's going down. How does it work?
So basically we take 2 parts and we clamp them under a piece of borosilicate glass usually, or some sort of a laser transparent clamping fixture. And that holds them together. And then the laser produces a melt all the way through the part. So the glass and the fixture kind of act as a sandwich to keep the material from bubbling up on the top. So we get a smooth weld, and then we produce a full melt through those surfaces.
I see. Very cool.
Yep. So if we jump ahead here, let's see, here is kind of the process comparison between the two. So in 1 micron, again, we don't necessarily need a clamping fixture. We just need to get the surfaces intimately contacting each other. And I should add a key point here. With the previous thermal processes we talked about, there's some latitude for variation in how those part surfaces come together. With laser welding, you need very intimate contact of the surfaces. So you've got to make sure your parts are good. If you have a gap at the weld seam, it's very possible that we won't be able to get a melt across the surfaces. So while laser is probably the most accurate welding method, it also requires the most quality control on your parts. It's a key point to keep in the back of your head.
Least forgiving.
Yes, yes, absolutely. So 1 micron, again, you can see we're shooting through the laser transparent, hitting the laser opaque, and then that molten puddle is radiating back through to the transparent part to produce a weld as it cools. And that's why it's so important that we don't have an air gap between those parts, because it won't radiate back. 2 micron is a little bit more forgiving because it's shooting all the way through. Basically, we clamp the parts up, we shoot through, we produce a melt, and then we solidify it.
From a cycle time perspective, one longer than the other, or?
Yeah, 1 micron is usually faster. That's that first key point right there, because we can do quasi-simultaneous. So what that means is, if you've ever watched a laser light show, right? They're using galvos to trace a pattern or an image so fast that it looks like an entire image, when in reality, it's one laser beam scanning around. We do the same thing with 1 micron laser welding. The galvo is moving so fast that we're hitting the whole joint, and then we can actually do collapse control. So that gives us the ability to melt down the parts with a little bit of collapse. And it's usually, somewhere in the neighborhood of 15 seconds of time, the time you engage the laser, melt, and hold. Sometimes faster, it depends on the parts that you're welding. And then 2 micron, again, both parts need to be clear. And it's a little bit slower process depending on the size of the part, because we make one slow pass all the way around. So maybe 15 to 30 seconds on a cycle. So which is better? It's kind of a bad question. Everybody always asks that. That's why I've added this slide. It's not that one is better than the other. It's which one is right for your application, and we offer both. So we'll make sure that we get the right one for you.
Got it. Boom.
All right. These are the kind of parts, we do a lot of lighting, we do a lot of medical components, but lighting is usually 1 micron, typically, again, clear to black. And then if you move ahead, I think I've got some examples of 2 micron welding, tubes, ports, clear components, a lot of medical applications. That's usually where we see 2 micron welding. And I added a couple extra slides in here. One of the questions with all these particulate free welding methods people ask me is, can I ensure that I have a good weld without ripping it apart and looking at my weld? And the answer is yes. There is a system out there called a TPMS system that we have a very close relationship with a vendor, and we'll install these systems in all of our welding machines. And basically what we can do is, using infrared thermography, we can get a picture of what we know to be a good weld, and we can set an infinite number of control points on that weld surface. And we can do this, like in thermal welding, we can actually take a picture immediately after the melt on both parts to make sure both parts are thoroughly melted before we join them together. And then with frictional and laser welding, we can actually take an image of the thermal bloom coming through the parts to make sure that we get, again, a consistent melt. Once we know we have good parts through other means of testing, we can match that up with what the proper thermal image is and make sure each weld that we get that thermal image every weld cycle. We can do this on sonics, we can do it on frictional, we can do it on thermal, we can do it on everything. So just keep that in the back of your head.
Wow, very cool. So what, so on a normal size, let's say a headlamp, what would be, or a tail lamp, what would be an approximate cost to add that assurance?
That's a tough call. It really varies depending on the system and what you're doing. Maybe somewhere in the neighborhood of, I really should talk to the vendor before
that's okay. That's okay.
Yeah, so yeah. What I'd rather do
the
is,
hardware cost is what it is, but it's the development cost.
There's a lot of application and support that goes into it. It's a significant investment, But again, we find the savings in quality control outweigh the cost of the system.
This looks like
I would say in the example of a sonic welder, it might double the cost of the welder. In the case of a thermal welding or vibration welding, it might be the cost of another tool that you're adding on.
Okay. This looks like a Hot Wheels box here. You know, remember that?
I don't actually know what that part is to be. I can venture a guess, but I'm not sure I can say without causing problems. So,
Sure.
but again, this kind of shows the company that we work with, Emitted Energy. I don't mind throwing their name out there. They're a great company, and they offer, you know, a standalone system integration and support, and we have a wonderful partnership with them. These things have really changed our capability and quality on all of our thermal welding. All right, well, that's probably all I have. Russ, I hope I touched on kind of what you were looking for today.
Oh, Paul, that was phenomenal. That was exactly what I think. I mean, I personally benefited from it. You know, hearing that information was super helpful for me. I know it will be for our customers over the course of time as they view this. This will be on YouTube. Of course, we'll share this with everyone there at Duquesne so that they can share. This is just wonderful information to have, and just super helpful. I know more. I'm smarter now than I was before, and that takes a lot.
All right, well, just keep in mind, everybody, we're out there to help. If you've got to put plastic parts together, Russ will get you to us, and we'll guide you through every step of the way.
Absolutely. All right. Thank you, Paul. Thank you, Vicki. Thanks to every customer that joined today. We'll be right back here next week for another Industry Cast. So until then, be safe and have a wonderful week. Bye-bye.